Very good afternoon friends, and in this video we are going to discuss about the electric field lines. And everyone knows that electric field lines are just mathematical model. There are no such lines that if you have a charged bodies, then from that the imaginary lines will be coming out. This is not a Spider-Man movie, friends. This is electric field. This is just a mathematical model to understand the behavior of the electric field. Electric field is just defined as the force upon charge, and it is defined as electric field is limit Q naught tends to 0 F bar over Q naught. This quantity is called as electric field. And if you just try to understand what does it mean, suppose if you have a positive charge here P and its magnitude is Q, and away from this you have a tiny charge Q separated by a distance R, then the electrostatic force, since both these charges are positive, so the force acting on this charge will be repulsive in nature, and that magnitude can be given as F bar is 1 over 4 pi epsilon naught Q over R square, and I just give a R cap, assuming that this R cap is the direction in this sense. Or if you want to understand it in a different way, then you can assume that this charge is placed at the center of a rectangular Cartesian grid, and this is the point A, and the position vector of this point with respect to this is R bar. I can write it as O bar is R bar. So the force here acting on this one is in this direction. This is positive, this is positive. Now the force upon this Q is 1 upon 4 pi epsilon naught. This is Q over R square R cap. This is your electric field. Now electric field, the electric field is also very much in the direction of the field. But suppose if you take another charge which is negative and at a distance of R1. So this is minus Q and the distance is R1. So the force on this will be acting towards this. Okay, so this is the direction of this. Now to understand this in a more better way, the designers or the mathematicians and the scientists came together to develop a mathematical model to explain that how you can understand the electric field lines easily, and they introduced the idea of the electric field lines. And electric field lines are something like that if you have a positive charge, then you can assume that the electric field lines are emanating from it and spreading outward, just like the light spreads out of a glowing lamp in all possible direction. Since those who understand the mathematics, they can understand that even if you draw a large number of these lines, then since they are starting from circle, so around this charge, these lines will be so thickly placed, and that indicates the strength of the magnetic field. But since it is a point, you always have that you move away from this, then the field lines will be separated a little farther from one another, and as a result of this you will have the weaker fields. And mathematically also the electric field lines follows the inverse square law, means if the distance of separation from the charge increases, then the electric field decreases. Now in the case of when you have the negative charge, then what will happen? Then you can assume that the electric field lines will be converging at that point. This is minus, so the field lines will get into and converge at this point. So this is the nature of the electric field lines. This is converging in nature, and here it goes like this. So the electric field lines are converging. Suppose if you want to have the uniform electric field, then you must have the parallel electric field lines and the evenly placed electric field lines. This we can obtain by introducing the charges on the plates. Like if I have a charge and if I spread positive charge on them, and there is another plate which have the negative charge on them, then the electric field between them will be parallel and evenly placed. This is called the idea of the uniform electric field. Okay. Now on the basis of the field theory, how do these fields communicate when there are two positive charges placed one from that's very close to one another? Then they both will have the different field lines, and how we can find how they will be communicating. This goes like this, outward, and here also outward, outward, outward. But you know that when two positive charges are placed, they repel each other. So here the electric field lines will become something like this, just like they are repelling. And this is the idea of the field theory, that when two fields, like the space around these two individual charges, both are same nature, so plus q, so when they repel, means the electric field around them, the electric field generated by them because of their charge, they repel each other and the electric field lines become like this. But how the communication will happen when these two charges are of opposite nature? Means if one is positive and other is negative. So from positive, the field lines will be scattering outside, just like the previous case. Here the field lines will be entering and converging at this point. Now what will happen between these two? So you can say it will be something like that. So the unique feature about these field lines are the two, that if the field lines are very closely packed, then the strength of the electric field is greater. If they are not that closely packed, it means the field is weaker. If these field lines are parallel to each other and evenly placed, we can call them uniform electric field. And if they are not parallel, just like these ones, then the field around them is not uniform. Now one more important point about the characteristics of the field lines is that no two electric field lines intersect each other, because if they do so, mathematically at the point of the intersection of these two field lines, you can draw two tangents, and these two tangents give you the two different direction of the field, which is not possible. So that's why the electric field lines are actually, they represent the direction of the electric field. Just drawing a tangent on them, you can find the field strength or the direction of those electric field lines at that point. So this is all for this now. Now I'm going to discuss about the idea of the electric flux. What is electric flux? Electric flux is just like, suppose if you have this electric field and if you place one surface, then how many electric field lines are going to intersect it? It depends on the position of this area element and also on the rotation of that one. Mathematically we can say that electric flux phi is the dot product of the E vector and the ds vector. Ds vector is the small area element. Now you all know that the area is a scalar quantity. Then how this area has become a vector quantity? Because I have placed a bar over it. Since area is a scalar quantity, it only has magnitude. Now how can I convert this area, which is a scalar quantity, into something which is vector quantity? Just by introducing the idea of the outward normal. Like, suppose if the electric field lines are coming from my camera, so now you see that this palm is the area element, and then since the electric field lines are coming from the camera to the palm, so you can assume that this, just the way I'm holding my hand, this is the normal, outward normal over the surface. Now just you see, so this is the area that you can call it as ds, and the direction of the pen which is coming away from the camera is the direction of the normal. So it means here in this condition you can say that it appears as if the angle between these two is same. So if I find out this is E dot ds, then you find that the phi will be called as E times ds cos theta. So this is the idea of the electric flux. Now I have to clear my screen and just give me the 10 seconds break, and then again I'll come back to you. Okay, now you assume that here you have a point, at this point a charge Q is placed. Now using the idea of the electric field lines, we can say that the electric field lines will be starting from this one and moving out of this. So they can be something like that. Okay, now you just assume that you have got a area element of this size, and of this size. Then the angle subtended by this is also called as solid angle, and its value is delta solid angle is the area element upon r square. This is the area of this. This is delta is small d delta. So this we call it as a solid angle. A solid angle. The plane angle, you have studied that the plane angle is just like if you have, this is the two-dimensional, this is arc. So its length is delta s. This angle is delta theta, and this is r. So you know that delta theta is delta s over r. So this is called the plane. This is two-dimensional angle, plane angle. You have studied in the circles. The angle is always subtended by the arc at the center, and this angle theta is delta s upon r. But this is a solid angle. Means you can assume that this is a football, and there at the center charge is placed. So this area element here is, now you say this area element, this area elements are, this area element is larger. So here this delta A and its angle R1 from here, and I call it as delta A1. This is delta A2, and from center this is R2 unit away from this. This is delta A3 upon, and this one is delta, the distance of separation will be R3. So in all these cases you'll find delta A over R1 square delta A1 is delta A2 over R2 square is delta A3 over R3 square. Now just assume that if I try to complete this sphere, just keep this in your head that this is a sphere. So this will be something like that. Then the whole angle, this will become 4 pi. Okay, it's 2 pi, it's not the 4 pi. This is okay. So this angle is complete, is called the solid angle, and that will be 4 pi steradian. This is a solid angle for the sphere. And now here if you complete this one, you get this one as 2 pi is the complete planar angle, and this is 4 pi steradian. So this is the idea from where the Gauss derived his theorem. What is the Gauss? Suppose, because the Coulomb's law speaks that when you are given the two charges, then you can find the distance between, and you know the distance between them, you can find the strength of the force and the direction of the force acting on the individual charges. Newton's third law is equal and opposite charges, equal and opposite forces there, like the forces always exist in pair. That is also true. Here in this case, now you see this is Q, and that is, now the idea is that using Gauss law, you can find the electric field of a charge confined at the center. Then in the, just let me clear the screen and then I come back to you to explain you the idea of the Gauss theorem.